What I mean is that that's where 0 is on this one. And if you're able to skip ahead, that's where 0 is on this one. So be looking for where those are on these graphs because we know that that's important. Also, I also want to point out, I give you a piece of information here at the beginning. I say to assume that the object starts at the origin. So at t equals 0, that's the initial position of the object. So I want you all to do number 1. I'm going to come by and check your work, and that'll kind of give me a baseline as to where I need to begin today. Let's try and collect some of the things we talked about on Friday, put them in one place, and see if we can apply them correctly here. Now, first thing I notice is that we're observing the object over a period of 10 seconds. That's the first thing I notice. So the very first thing I would expect, and if you want to be able to get all the credit for stuff like this, is your graph should also be for 10 seconds. And notice you label the horizontal axis correctly, giving units. Without that information, it's useless. In this case, the vertical axis is the position. I'll label it correctly too. But the horizontal axis should match up. It should be the same as the other graph. Now, coming back over here, the first thing I notice is I have 3 sections of the graph. Do you guys see 3 sections? The first section shows that the object's velocity is 0 for the first 2 seconds, suggesting, I hope quite clearly, that there's no displacement over the first 2 seconds. However, the second interval, which appears to be about 4 seconds long, has a clear and obvious area, reflected in the 2 meters per second velocity over a span of 4 seconds, giving us a positive 8 meters displacement. So the object's position changed by moving forwards 8 meters. In the next interval, my area is bounded by the curve and the horizontal axis. Careful how you do this. The axis is key. The curve is the other boundary. So some people kind of shade all of this in, but that's not true. It's only the area between the curve and the axis. This is also a 4-second interval, but in this case, the height, length, whatever, -1 meter per second. So this section has a displacement of -4 meters. So colloquially, the object stayed still for 2 seconds, moved forwards 8 meters over the next 4 seconds, and then moved backwards 4 meters over the last 4 seconds. So in trying to draft what this should look like, the first thing I'm going to recognize is that the object starts from the origin, marking that as my starting place. The object's going to move forwards 8 meters. So if I want as much credit as is possible for drawing this graph, I need to use as much of the available graph space as possible. So I want to try and make 1, 2, 3, 4, 5, 6, 7, 8. I want to use as much of the graph as possible. I know the object travels outwards 8 meters, so I'm trying to get 8 as close to the very top of this graph as possible. I know that my graph is never going to dip into the negative position. It moved forwards 8, backwards 4. Now look, some of you had your object go to the 8 meter mark and then backwards to the -4 meter mark, because that's what you calculated. So you figured that's where it is. That's not where it is. Each area is a displacement, a change in position. So although for the first 2 seconds, the object stayed in place, over the next 4 seconds, the object will move out to the 8 meter mark. there-ish. Now, from here, it moves backwards 4 meters. So this is the 4 meter mark. 4 meters from 8 meters puts it at the 4 meter mark. I have to connect these dots using something that's reasonable. The slope of the position versus time graph is velocity. So when I look over here, I notice the velocities are constant. So over here, my slopes have to be constant. For example, in the first section, the object doesn't move at all. So its velocity is 0. But it's constant for those 2 seconds. Next, when I go from 2 seconds to 6 seconds, the object's position goes from 0 to 8 meters, but its velocity during that time interval is constant with a slope of 2. So I need to draw a straight line. I must be intentional with this line, which means the grader should see that you used a ruler to draw it. That's what intention means. When it goes backwards, it has to have a slope of -1, and it has to be a constant slope. This is what I expect it to look like. There are discontinuities in this graph, abrupt changes in the velocity and therefore abrupt changes in the slope. But this is what it should look like. We're batting just under 70% in here. So perhaps with your newfound knowledge, you could apply it real quickly here, 2 minutes. I know some of you have already done it. All right, look, 2 minutes. So I don't want to spend a lot of time. I should come by and take a look, but I'm thinking that probably you're getting acclimated based on what I saw before. Most of the mistakes were pretty straightforward. I see, hold on. I see 3 separate areas. I see an area here with a displacement of 20 meters, 5 meters per second times 4 seconds. I see an area here, displacement of 5 meters in the negative direction, -1 meter per second for 5 seconds. And I see an area here with a displacement of -3 meters, because it's -3 meters per second for 1 second. So over here, starting at the origin, I place a dot at 20 meters, 4 seconds away from the origin. Then I walk it back 5 meters to the 15 meter mark, and I take 5 seconds to do that. And then I walk it back another 3 meters to be at the positive 12 meter mark. Connect them all with straight lines, because this is supposed to indicate that the velocities were constant in each interval. Questions about this? Yes, sir?
So what's this circle like on ours or yours?
I'm circling them because it captures the line and moves it with the page with me. So if I don't do that, then the lines stay in place and the page moves underneath it. So no, I don't need that. Is this good? Because trust me, this is the simple stuff. The hard stuff is coming. All right. And I want to go forward. So what I really want to talk about are cases that are more natural. And this is a more natural case. This case is different than what we've seen before. In the prior cases, I've given you guys things that you could probably reason out if you wanted to. Meaning the objects had constant velocities. So 2 meters per second meant that you could count off how far it traveled if you know how long it's traveling that speed for. This is an example of an object whose velocity is not constant. which means the amount of distance it covers in the first couple of seconds is much different the amount of distance it covers in the next couple of seconds. Because in each second, it's traveling faster, therefore covering more distance. Although that's all true, it's still just a velocity versus time graph, which means that all the features of the velocity versus time graph still apply. The area under the curve will tell me displacement, and the slope of my position graph will be the velocity and the values of velocity at any point on the graph. So how do we use this information? Well, we're going to use it the same way we used it before. To make a position graph, I need to figure out what the object's change in position is. And I'll do that by figuring out what this area is. Lucky, this shape is pretty easy. I've moved from a rectangle to a triangle. Third grade should give you sufficient access to how to calculate the area of a triangle. If not, freshman geometry or 8th grade geometry will do the same thing. So, how do I calculate the area of a triangle? You can just yell it out. Thank you. 1/2. Base is 10 seconds, because that is the time interval portion. Height, 20 meters per second. So it looks to me like the displacement over the interval is 100 meters. And it is positive. Any question about that? Yes, sir? I don't know yet. And we love to use words to which we don't know the meaning. I say we collectively because I do the same thing. So let's see what that would mean here. First, 2, 4, 6, 8. That's not using the whole graph. Let's do better. 2, 4, 6, 8, 10. Try to use the whole graph as much as possible. This is time in seconds. I know the object is starting at the origin, and this is the position of the object in meters. Now, I don't know as much about the middle. I don't have as much information, but I do know that after 10 seconds, the object will be 100 meters away. Now that means over here, now I have to find a way to connect these two dots, and it will not be a straight line. Because a straight line would indicate that the velocity of the object was constant. But we know from looking at this graph that the velocity of the object was constantly changing. However, I know more than that. I know that at time equals 0, the object had a velocity of 0. That means that at time equals 0, the slope of my graph is 0. So this curve had to start flat because it had a velocity of 0. Well, at time 10 seconds, the velocity was 20 meters per second. So at 10 seconds, the slope has to be positive and 20. Well, 20 is pretty steep, and positive is definitely in that direction. I don't have to have a firm scale here. But I do have to know that a smooth curve must connect the first dot to the last dot. I know that because there's no discontinuity in this graph. And because there's no discontinuity, the curve over here must be continuous. So no abrupt changes, no corners in my graph, That means a smooth curve must connect the two dots. So break out your artistic skill set here. And try and give me your best curve through the points. Now, does that make it exponential? I doubt it. I can't prove that yet. Well, I could, but I don't know that we're ready for that today in the next 2 minutes. But exponential is a word you guys tend to use without understanding its full meaning. An exponential function would be a function that equates y with the e to the x. But I think that any of these graphs would look similar if you didn't know their scale. Correct? So it's hard to know if it's exponential or quadratic or x cubed or x to the fourth or hell, x to the 10th. It's hard to know. Because if you put any of those into Desmos with the right scaling, you could probably make it look like this. So I don't know if it's exponential. I think I can prove which one of these it is, but I don't think I can do that till tomorrow or the next day. So I don't want to use the word exponential for this purpose, because it actually has a specific meaning in my class. So I do know it's curved, and it's concave upwards. And I think that's reasonable. Does that make sense so far? So there are 2 minutes left. And with that thunder out there, you're going to want to hurry to your cars. Think you guys can do this one tonight? I remind you, this is where the origin is. You don't have a lot of time, and so I want to leave you with something. This is an area. This is also an area. Remember how area works. It's the area of the curve compared with the horizontal axis. Try this one tonight. If you catch on to this, you can do your homework. If you don't catch on to this, you might need me to help you with your homework. That doesn't mean that what you need to do this is obvious. So let's see if we can't put some ideas together. Is that fair enough? I don't think there's anybody in the room who didn't figure out that this was positive 125 meters. Right? One half base times height. And then similarly, this negative 125 meters. Again, 1/2 base times height. Any question about any of that? Yep.
I couldn't figure out if it was like 5.5 at the time. Like, where's the intersection at? Is that 5.5?
Nope, it's 5. I see complete symmetry, and this sucker is coming right down in the middle, and that's got to be 5. Because it's right in the middle between 4 and 6. Not trying to trick you. Perhaps I could have done a better job of laying out the time. So here, we start at the origin. So all of you who have one of these, start at the origin. How do I know to start at the origin? That's how I know to start at the origin. I told you to. But okay. Not trying to rub your nose in it. Position in meters, time, seconds. I'm going to hit the 5-second mark and the 10-second mark. Good so far? After 5 seconds, the object was displaced 125 meters in the positive direction. 125. Any question about that? Excellent. After another 5 seconds, the object was displaced negative 125 meters from here, which places it there. All right. Good. Now, how do we connect these three dots together? That's a critical discussion too, because the slope of the position versus time graph is velocity, but the velocity is always changing. So let's pick a couple of guide points and use them to get us a picture of what the slopes should look like. Let's start at 0. At 0, the velocity is 50 meters per second, which means the slope of my line at 0 is steep and positive. 50 is a big number, so steep slope, and it's a positive number, so it must be inclined with a positive slope. Seems like the next point to use will be this one, agreed? So I'm going to go take a look at the slope at 5 seconds. That'd be this bad boy right there. What's the velocity at that moment? 0. So my slope there should be 0. Excellent. So this looks like a good one to use for me. How about you guys? All right, so I'm going to slide back over here. What is the velocity at t equals 10 seconds? Looks like it's negative 50. So that's going to be steep and negative. I need now a way to connect these dots together that shows a smooth transition, right? I'm noticing over here that the transitions are uniform, right? There's no abrupt changes. There's no kinks in the graph here, which would produce discontinuities in the other graph. So I should connect these together in a way that is symmetrical and consistent. I don't know what that is. I mean, I could probably figure it out, but we're not there yet. But this you can do. Any question about that? I want to add to this today, but did I use any? Let's define acceleration. Acceleration is the rate of change of velocity. I'm going to define it like 5 different ways. That's the first. Acceleration is the rate of change of velocity. It is a rate. And I'm emphasizing that word because there are a lot of rates in science. A rate tells you how fast something changes. Velocity is a rate. It's the rate of change of position. Acceleration is a rate. It is the rate of change of velocity. So when I describe a rate, it's about something that is being compared with time. Again, there are lots of rates in nature. Anytime time is on the horizontal axis of a graph, the slope is a rate. So I'm using the word rate, R-A-T-E. Acceleration tells you how quickly an object's speed changes. It also tells you in what direction its speed changes. So acceleration has critical attributes. But the thing about acceleration that's important is that acceleration is how an object's motion is changing. That's what you really need to understand. Acceleration is about change. Now, you can, with the information you have here and your advanced knowledge of mathematics, figure out what the acceleration is. So if you would please, use that advanced knowledge and get a value for acceleration. I use numbers that would be easy, so hopefully they are. We done? We should be. What you got? Yeah.
Minus 10 meters per second squared.
Who got minus 10 meters per second squared? That's what you should get. Pretty straightforward. Rise over run. All right, it's a slope. So if I chose this point and this point to calculate slope, I would indicate that it went from 50 to 0. So 0 minus 50 meters per second in a time of, well, it looks like 5 minus 0 seconds. So negative 50 divided by 5, or negative 10 meters per second per second. I'm writing it like that not to make it more complicated, but understand units in physics are all compound units. They're all a mess. So if you write it like this, it tells you how fast the velocity changed. For each second, the object's velocity decreased by 10 meters per second. So if at 1 second its speed was 30 meters per second, at the next speed it would be 20. You follow me? It's decreasing 10 meters per second with each second that progresses. Yes, you could write this as negative 10 meters per second squared. That would be just fine. But don't forget what it means. It's how fast the meters per second are changing each second. Now, is this object speeding up or slowing down? I love asking that question because I've asked it 4 times today and I've gotten the same response in 4 classes, except for 6th period, which I heard this. Making them less fun to teach. Like, I don't care if the answer's wrong. I just care that you try. Play the game.
Is it changing direction instead? Is it doing both?
I think it's doing both. If we start out looking at this, would you notice that it starts out at 50 meters per second, and over the course of a couple of seconds, it goes from that to 0? I define that as slowing down. But then it's at 0, and over the next couple of seconds, it starts increasing its speed until it's traveling at 50 again. I'd call that speeding up. So the first thing that should be in your notes is that this direction might not be telling you whether it's speeding up or slowing down. You'd like it to, but it does not. Acceleration does not tell you if something is speeding up or slowing down. You want it to. It's what the word seems to mean, but that's not. Acceleration tells you how the velocity changes. In order to know whether something's speeding up or slowing down, you have to know what it's doing first. I'll say that again. Acceleration doesn't tell you whether something is speeding up or slowing down. It tells you how the velocity changes. To know if it's speeding up or slowing down, you have to know what it's doing already. The acceleration for this ball is negative 10 meters per second, which means I can tell you this, it's changing in a negative direction every time. The velocity is becoming more negative with every second. That's all I can tell you. That doesn't tell you whether it's speeding up or slowing down. It just tells you the velocity is becoming more negative with each second. Can somebody give me a colloquial example of what this graph is telling us? Like something real, tangible. Yes, sir.
Like a ball's going up the ramp and then it stops kind of and then rolls back down.
Ball's going up a ramp, stops kind of, rolls back down. What do y'all think?
Yep.
Not terrible. You could just throw the ball in the air and it'd do the same thing, right? Throw the ball up, it goes away from you for a while, comes back towards you for a while. Does that seem reasonable? Let's consider what this really is then. Let's have over here, what's the slope? Right here in the middle. Still negative 10, right? That point has a slope. That slope's not 0. The slope at that point is the acceleration, so it's the ball thrown in the air. So I have, here's you. Looks just like you. And you're going to throw a ball in the air. I can't just do this all in a straight line. It won't look right. So I'm going to make it like little sections, if that's all right. Meaning like, here's the ball a few seconds later. Here's the ball a few seconds later. Here's the ball a few seconds later. A few seconds later. A few seconds later. And back to you here. That good? You follow what I got here? So it's clear from our problem that the object starts with a velocity that is positive. So let's say that up is positive, because the ball has a velocity of 50 meters per second when we first look at it. Make sense? After a couple of seconds, the ball's velocity is less. Agreed? After a couple of seconds, the ball's velocity is less again. Agreed? It stops, and then it's going the other direction. That makes sense? And after a little bit, it's faster in the other direction, eventually making it back to where we started. So I've drawn the velocity with an arrow to indicate the direction of the velocity, and the length of the arrow indicating how big the velocity is. That is a way you can write a vector, is an arrow where its length and direction give you the size and direction of the thing you're trying to mimic, the velocity. Acceleration is negative the whole time. So consider this. When you first released the ball, the acceleration was downwards. What did that do? That made the velocity a more negative number. Right? It made it smaller. It chipped away at the velocity. So a moment later, the velocity was less. Still have an acceleration pointed downwards though, which is going to make the velocity a smaller number. A few moments later, still have an acceleration downwards. The acceleration was 10 all the way up. But then something happens. The ball stops. What's the acceleration when the ball stops? You can just say it. If you're thinking 0, you're wrong. And I know some of you are. The reason I know that is for the last 20 years, I've put that on a test, and some of you get it wrong. But when I look at accelerating, even though it's not moving, and that acceleration is still negative 10. The knee-jerk is to say when the object stopped, the acceleration is 0, but that's wrong. If that were true, and the acceleration was 0 when the object stopped, it would never start again. And it would just stay there. There has to be something that brings it back down. So it's still accelerating downwards, even though it stopped for that instant in time. And of course, the acceleration is still pointed downwards. Now the acceleration is speeding it up, but it's still doing the same thing. It's making the velocity more negative, which it was doing the whole time. Acceleration is a vector. It has direction. It points. And it's in the direction that the velocity is changing. I would strongly encourage you to consider that, especially as we get into more two-dimensional and three-dimensional examples. Acceleration has direction, and it's in the direction in which the velocity is changing. It points. So don't lose sight of that. That's an incredibly important detail. What acceleration doesn't necessarily tell you is whether something is speeding up or slowing down, even though that's what you kind of think acceleration's about. It's just different than that. It's a little more complicated. Let's try an example. Now, I'm about to produce an example, and I've been using the same example all day because my students have been disappointing me. But this class has not been disappointing me. This class has been solid. But I'm still going to give you the same example because that way my notes are consistent across the day. But this is the mean example. There's an easier example I could have eased into. But I've decided, to keep you guys in the same position as everybody else. If you talk to your friends in the other classes, you'll be stuck with the same kind of thing. So here's what I want you to do. I want you to basically just answer the same question we've been doing. I'm going to give you a situation, and I want to see if you can employ your reasonable skills to tell me what's happening. What I really would like to know is the object traveling away or towards, speeding up or slowing down, what's the displacement? What's the acceleration? And, since you've got all sorts of smarts, maybe just sketch out a quick position graph. All right, here we go. There you go. Try that out. Seems like slowing down is the right answer there. 20 to 0 in 5 seconds, slowing down. But it's traveling with a negative velocity the whole time. In fact, if I look at this displacement, 1/2 base times height, I'd get 1/2 times negative 20 meters per second times 5. Negative 50 meters. So it traveled backwards the whole time. It traveled in the negative direction the entire time. So assuming it started from the origin, which is not an unreasonable thing to do since that was the whole worksheet yesterday, you may have started it somewhere else, but I didn't give you a starting place. Even so, what you draw next should look the same. So I see a slope of negative 20 at the start, which means I should have a slope that is negative at the start. After 5 seconds, the object has traveled negative 50 meters. And at 5 seconds, the slope should be 0. The velocity is 0, so the slope should be 0. I'm not trying to trick you. Any questions here? Anything here that's not, I've indicated like little partial curves there. I've considered the slope on the position graph. I'm noticing that there's no discontinuities or no kinks in the graph that would cause a discontinuity in the position graph. So there it is. That's it. I didn't calculate the acceleration. We should. Although this object is slowing down, I go from negative 20 to 0 in 5 seconds. That seems like an acceleration of 0 minus negative 20 in 5 seconds, or 4 meters per second squared. The acceleration is positive. The velocity is becoming a more positive number. It started negative, but with every second it's becoming a more positive number. Yes, sir?
When we write acceleration, does it matter if we say meters per second squared or meters per second per second?
Nope, doesn't matter at all. I will switch back and forth between them. When I type it, it's easier to write meters per second per second. Maybe try another one? Yep.
So when you're saying slowing down, you're going from like negative 20 meters per second to 0? Is that, because when I see like negative going up, I think it's like speeding up.
And you'd be wrong. Have you ever been in a car traveling backwards?
Reversing, yeah.
Did you ever have to slam on the brakes?
Yes.
So would you say that the car was slowing down?
Okay.
You're traveling backwards, but you still slow down, right? Yep.
For the position versus time graph, do you care like how our arc looks or just that it's arced?
I care that it's concave up. If it's concave down, you're wrong. Yep.
In this, when you say traveling away or towards, I was confused on like.
I think that one is ambiguous, and intentionally so. It's hard to say away or towards, right?
We don't know.
But we know that it's traveling in the negative direction. So probably away or towards might need to change to be whether it's traveling in a positive direction or a negative direction. If I think of a number line, I would say this is traveling in the negative sides of the number line, towards the negative numbers. Does that make sense? The fact that it started at the origin means it traveled all in the negative numbers. But if it started 20 meters away from me and was traveling in a negative direction, it would be traveling towards the origin. You follow what I'm saying? So I think this graph shows something traveling away from the origin. That's for sure. I don't micromanage notes, hardly ever. Well, never. To me, it's a skill that you need to develop. But I want to give you at least a little bit of organization here. We are taking and comparing the information presented in velocity graphs with position graphs. I probably should put velocity versus time and position versus time, so excuse me for trying to be hurried about this. We talked about several things. This is not an exhaustive list, though. There are other things you'll have to add to this as we go. But there are some things that we did make very clear. You know, a velocity graph tells you how fast and in what direction the object is traveling. Over the interval. Now, that's just a definition of what the graph shows you. That might not be very much. We know, in addition to this, that the area under the curve, the area bounded by the curve and the horizontal axis, represents the displacement of the object. Now, displacement's vocabulary, so I like to be very specific whenever a vocabulary word makes its appearance. Displacement is defined as the vector change in position. Now, a third thing was brought up, but it's not what a velocity graph tells you, it's what it can't tell you. It can't tell us position. It never tells us where the object is. It tells us where the object goes, but it never tells us where it is. And that's because it can't tell us where the object began. It doesn't give us information about the origin or the starting position. So it tells you how much its position changed, tells you how fast it did those things, but it never tells you where the object is. For that, you need a position graph. So a position graph gives you exactly what a position graph can. Where is the object over your time interval? It clearly gives you the position. And of course, it can tell us more things than that. We know that the position graph has more information embedded in it, the slope. Excuse my messy writing there. Velocity is a vocabulary word. So the slope of the position graph is the velocity, which is defined as the rate of change of position. You know, it's how fast and in what direction. So this was what I wanted you to take away from Friday. And some of this I would have expected you guys came to class already knowing, but maybe not all of it. So coming back over here, answers are here. Okay, everything you need to do this right here. However, it's not here. So I know this sounds terrible to say, but you want to sometimes do things that aren't reasonable because you just don't think they're supposed to be like that. Everything we're doing is right here. It is reasonable. And there's a rule. Follow the rule. Whether you want to believe it or not, follow the rule. The position graph can tell you velocity, it's the slope. The area of the velocity graph is the displacement. Positive and negative is important. So now let's add something here. I want to add something new. Point number 4. The slope of the velocity versus time graph is the acceleration. The slope of the velocity versus time graph is the acceleration. I underlined it. That's a big vocabulary word. The most important vocabulary word of this semester. It's critical to your understanding of physics is to understand acceleration. This is not a definition. I want to point that out too. I'm not defining acceleration. I'm just saying that a quality of a velocity versus time graph is that it can tell you the acceleration. I'm going to define acceleration when I flip back. So here. Anything? I'm just trying to make sure. All right, so there's only 4 minutes left. You have quite a bit upon which to do your homework, but let me at least put one thing in front of you that the other classes had a chance to see. Can you tell me what the displacement of this object was without breaking it up into multiple areas? There's a shape here. So I see you have your hand up. I'm going to ask an intermediate question. Can you tell me what shape we should go with?
A triangle, right?
No. Yes, sir?
A trapezoid?
A trapezoid. I see a trapezoid. Do you see a trapezoid? I see 2 parallel bases, which is a trapezoid, and 2 other sides. That's a trapezoid. Do you know how to find the area of a trapezoid? Go ahead, RJ.
Isn't it 1/2 times the first base and the second base, and then you multiply that by the height?
That's exactly how you would do it. So 1/2, sum of the bases times the height, that's how you find the area of a trapezoid. So for this one, pretty straightforward, 1/2, 15 plus 5 times 4, 40 meters. This object traveled forwards 40 meters. Yeah, I know you could break it up into a triangle and a rectangle. Don't. I want you to do a trapezoid. I have purpose for that. And you can figure out the slope. This object is slowing down, but acceleration is also negative. You good?
Yeah.
You can go.
Okay, I can-
Yeah, go.
Okay, I'm so sorry.
The money's sitting out, right?
Yes.
Okay. Nobody go to the back of the room. Now, I put this up there for a purpose, and that is because I want to show you this one. You might be inclined to treat this like two triangles, and there'd be nothing wrong with that. I want to prove you can treat this like a trapezoid. This is a non-Euclidean trapezoid. It has occlusions in the middle. But it's what you would get if you took a trapezoid like a sunshade and folded it over. You guys know the kind of sunshades I'm talking about? If you did that, that's the kind of trapezoid you'd get. You can still find the displacement with 1/2 sum of the bases times the height. Now, you should prove that to yourself. You should do the two different areas and prove that I'm right. But I am right. I need you to prove this to yourself before tomorrow. Now look, you can do a lot of your homework now. You should really attack it and make sure you've got a bunch of it done. We're picking up here tomorrow with an opportunity to take a look at some of your homework questions.